Hello, I'm Nate Sammons, a principal architect with Nasdaq, and today I'm going to talk about our data warehousing and analytics system, which we originally built on Redshift and have now extended to use EMR and S3. Throughout this talk, I'm going to focus particularly on security. So first, a quick introduction to Nasdaq, if you haven't heard of us. We invented electronic trading more than 40 years ago and are now the world's largest exchange company. We own and operate 26 markets globally, and our software powers not only our own exchanges, but over 100 customer marketplaces in 50 countries around the world. By operating our own markets and powering customer markets, we're making the world's capital markets more transparent, more efficient, and better, essentially. We're a public company listed on Nasdaq and are part of the S&P 500 index. In this session, I'll discuss our motivations for extending that Redshift warehouse with EMR and S3. I'll talk about how our data ingest system works. I'll talk about how we query encrypted data stored in S3 using Presto and other Hadoop ecosystem applications. I'll talk about how we manage schemas and how we do data migrations. And finally, I'll discuss future directions for our data warehousing efforts. First, let's take a look at the current state of our system in Redshift. So we've discussed our Redshift efforts at previous reInvent conferences, but just as a review, several years ago we transitioned from an on-premise data warehouse to Redshift, and we haven't looked back since. There's now over 1,000 tables that we manage in that system, consisting of data from hundreds of different sources inside our company. We're adding new sources all the time, and this database stores nearly 2 years of data at this point. We add around 7 billion rows a day, sometimes considerably more depending on market volumes. So we never want to throw anything away. To that end, we've recently expanded into a 23-node DS2 8x large cluster. And I can definitely say that the DS2 is a very welcome change from the DS1. It's not often that you can double your CPU and memory without additional cost. We're now at 828 virtual CPUs, almost 5.5 terabytes of memory, over a petabyte of local disk spread across that cluster, yielding some 368 terabytes of database capacity, and 92 gigabytes a second of aggregate disk bandwidth. We've been resizing this cluster roughly once a quarter since we started, and it now stores just over 2.7 trillion rows. That's made up of approximately 1.8 trillion rows from external sources, and an additional 900 billion rows of aggregates and otherwise derived data. We have 90 tables with over 1 billion rows each, and 8 tables with over 100 billion rows. And our largest single table by row count contains more than 370 billion records and consumes just over 20 terabytes of disk space. So if you do the math, that's actually just 59 bytes per row, which is a good reminder that you should get your column encodings correct in Redshift because it can help drastically with storage space. So what makes up all of this data? We pull data from hundreds of different sources inside Nasdaq. Some are databases that we scrape daily. Others are just CSV files produced from stream captures off of our exchange software. This warehouse grew out of a rewrite of our billing system and contains data from all 7 equities, options, and futures exchanges that Nasdaq operates in the United States. This data includes mainly orders, quotes, trade executions, and other so-called market tick data. But it also contains security master information, which is basically metadata about each symbol and instrument traded on those exchanges, as well as membership information about the firms making those trades. This data is used to drive a SOX-compliant billing system, which charges for every trade on our main equities and options exchanges, and we're rolling that billing system out to the rest of the exchanges operated by Nasdaq. We also support surveillance workloads for policing activity on our exchanges, as well as economic research work and other activities around billing models and other research activities. All of this data is highly structured and consistent, derived mainly from actual trading messages sent to and processed by our exchange software. So I've long maintained that data actually obeys many of the same laws as gases, specifically that data has a tendency to grow to fill any container that you attempt to place it in. This graph shows rows ingested each day over the last year in billions. You can see that we had a peak of 14 billion rows in early October 2014 because of market activity. This was actually our peak ingest day for all of 2014. You can see that Thanksgiving is a fairly quiet period, followed by a spike in activity leading up to another quiet period over the Christmas holiday. Most of 2015 was hovering in the 6 to 8 billion rows per day range, and then on August 24th, 2015, we hit a new high watermark by a pretty wide margin. Chinese markets dropped sharply that day and led to a very volatile week in US markets, driving a lot of traffic into our exchanges and thus into this warehouse. Our daily average is right at 7 billion rows, and that day we processed nearly 20 billion rows. So this brings us to why I want to extend this warehouse into EMR and S3 in the first place. Redshift is great, but resizing a 300 terabyte warehouse is not instantaneous. The new DS2 nodes are much faster at resizes, but it's still an over-the-weekend type of activity, and it has to be planned and managed by our operations group. A lot of this data is also, that's stored in this warehouse is also accessed very infrequently. So it doesn't make sense to pay for always-on CPU and disk to support data that you're not using every day. And particularly since no one wants to delete any data just in case, data is going to fill any container that you place it in, so why not place it in a container that automatically grows on its own? So here's how we're extending that warehouse. The main goals for this project were to create a secure, cost-effective, long-term data store. We don't want to have to throw anything away, while at the same time, we don't want to spend a ton of money to keep that data around, especially if it's not being used every day. SQL is really king at Nasdaq, so whatever solution we come up with must at least support a SQL interface for everything. And in addition to SQL, we want to support new and fancier analytics systems and query mechanisms. We'd like to be able to use Spark, apply machine learning, and use any other Hadoop application all on top of a common storage layer. We'd also like to cap the size of our Redshift cluster so that we don't have to keep resizing it every quarter. And finally, we want to be able to manage our storage and compute resources separately. This is partly because we want a good way to charge internal departments for their CPU time, and partly because we want to be able to isolate compute workloads even though they're working on the same data sets. We also want to be able to allow anyone to order up as much CPU as they like, or at least as much as they can pay for, and not have any one group able to monopolize the entire system from a compute perspective. So here's a high-level overview of the solution that we came up with. These diagrams can all be generally read left to right, top to bottom, and anything contained within the dashed blue lines are systems running inside Nasdaq data centers. Everything else is assumed to be in Amazon. So we have systems inside Nasdaq which write data into a temporary bucket in S3, which is then loaded into Redshift using copy SQL commands. For some data, we perform transformations and aggregations inside Redshift, and then unload those results back to that temporary bucket in S3. In all cases, original data and aggregates, we process that CSV data from the temporary bucket to produce Parquet files, which are stored in a separate S3 bucket for long-term storage. Presto, running in an EMR cluster, is then used to query data stored in those files in S3. This transformation into Parquet is currently being performed in a Nasdaq data center. However, this is a stopgap measure until we move this data ingest system into EC2, which we're planning to do in early 2016. And in both cases, SQL clients access these databases directly through JDBC. So Redshift continues to have an integral role in this new system. For us, everything lands in Redshift first. We're a very SQL-centric shop, and this entire system evolved out of several previous generations of on-premise SQL warehouses. As a result, we also have many groups that have tight SLAs on reports and other activities that are all dependent on Redshift. So it's our first priority, and it gets all the data first. Additionally, we don't want to have those data loading activities for Redshift run into the next business day, because data loading and query activity can compete for compute resources, and it'll slow down queries in that Redshift cluster. We perform those transformations and aggregations in SQL because, like I said, we're a SQL-centric shop, and it's very easy. That transformed data is then loaded back into S3, where it's processed and converted into Parquet. So earlier, I'd mentioned that one of the goals for this project was to decouple storage and compute resources. This is a major design tenet for us and allows us to manage those resources independently. At the same time, we can experiment with new apps without worrying about incompatibilities or compute contention or anything like that. And given that this is primarily a long-term historical archive, almost by definition, a huge amount of that data is going to be not accessed frequently. And in practice, access drops off very dramatically. Yesterday's data is used extensively, as is month-to-date data for billing and other purposes. We do get occasional requests for data dating back months or even years, usually as a result of a regulatory inquiry, but these are by far the outliers. That being said, all this historical data needs to be online and accessible at all times, so offline backup systems like tapes and that sort of thing are just not applicable. We also have a number of historical databases inside our company with data dating back to the late 1990s, and all of that data is in the process of being loaded into this system. Ultimately, we'd like to provide one-stop shopping for all historical needs for data inside our organization. Another benefit of decoupling storage and compute resources for this warehouse is that we're able to provide transparent cost allocations to our clients. Each client or department will get their own AWS account for their own use. Those departments can run as much or as little compute as they like, and they can balance speed of execution with cost on their own. Heavy compute users can run a large cluster and throw a lot of CPU at a problem, while lighter customers can still get their work done, and the two won't trample on each other. Those clients don't even need to be running the same query mechanism. So one could be running Spark, another could be running Presto. The S3 storage costs are shared, and the variable costs of running those compute clusters are passed directly through to each department's cost center. So let's take a closer look at the data ingest system, which makes all of this data available each day. Here's an overview which focuses on the left-hand side of the previous diagram. And again, this diagram can be read left to right, top to bottom. Inside Nasdaq, our data ingest system reaches into other systems and retrieves data. That data is staged locally on the ingest server, where it's compressed and validated. We have our own key management system, which I'll talk about later. It's used to generate and store all of the encryption keys used throughout this system. Compressed encrypted data is uploaded to S3, where it's processed by Redshift. This diagram also shows the addition of a Hive Metastore, which obviously isn't part of a Redshift deployment, but is integral to various Hadoop applications. Once data is loaded into Redshift and subsequently encoded for long-term storage, we alter the Hive schema in that Metastore to declare new tables and new data partitions for each day's data. For this data ingest system, we've built an in-house workflow engine to orchestrate all of these activities. This system is backed by a MySQL database, where we maintain the current state of over 40,000 workflows that are executed each day to maintain data and load it into this system. That workflow engine maintains all of the scheduling and dependencies between workflows and ensures that everything runs smoothly every day. Care and feeding is performed through a management GUI, where we can perform root cause analysis to figure out what happened with failed items, whether that be bad data that we received or some other kind of issue. This system is currently running on-premise, and like I said, we'll be moving to Aurora and EC2 in 2016, where we'll be able to use S3 as temporary storage space. Moving that system to AWS should allow us to more easily handle volatile market periods like we saw in August, without needing to provision excess compute and storage resources on-premise. So elastic computing really is great. Separate instances of this workflow engine also orchestrate daily billing runs, produce reports, and perform all sorts of other activities on data loaded or derived from this system. Most of those 40,000 workflows that we perform each day consist of some combination of these steps. We retrieve data from various other sources. These sources might be a database table that we query, or a set of or a collection of files that we're expecting to find on a file server somewhere, or a web service that we need to call. The vast majority of this data is in the form of simple CSV files, which are generated off of data streams coming from our exchanges. That data is validated, mostly for completeness, and then converted into CSV files and manifests suitable to be loaded into Redshift. Data is compressed and encrypted before it's uploaded to a temporary location in S3, and then we copy it into Redshift. In our large table cases, we stage a number of these copy operations throughout the day into S3, and then we merge a set of manifest files at the end of the day so that we can issue a single copy command once our nightly processing window opens. This allows us to do some processing throughout the day and get ready for our nightly loads without affecting anything in Redshift. Once that data is actually loaded into Redshift, transformation and aggregation operations kick off automatically. I usually think of these workflows as a very large tree, where the leaf nodes are individual file retrieval operations, and then the branches and trunks are progressively more and more aggregated data. Once the Redshift load and transform operations complete, corresponding S3 ingest workflows are also automatically triggered. These workflows are driven off of the DDL retrieved from Redshift for each table being processed. This is an easy way for us to detect schema changes, since we're not always notified by upstream systems of those changes. We manage a local database where we track Hive schema definitions, and I'll talk about that more in a few minutes. If a schema change is detected, we increment a version number for the table defined in that Metastore, and then we automatically ingest new data with a new schema into a new location in S3. Now, under normal circumstances, we're actually just adding new data partitions to existing tables, since we don't actually do migrations all that often. So we just modify that Hive Metastore, and we're done. So now that we've had an overview of how that ingest system works, let's talk a little bit in more depth about data security and encryption. Security is our #1 priority at all times. Everything we run in AWS is inside a VPC with lockdown security groups, network ACLs, etc. Each system should only be allowed to talk to specific other systems, and we don't have any blanket policies that allow traffic from the internet or the rest of the universe at all. We run our apps using credentials tied to least privilege IAM roles, and that applies to both applications using APIs and humans interacting with the console. We use MFA tokens, at least for root credentials on each account, if not for all of the humans involved. And you should see SEC 302 for more pointers on IAM. It's a really good talk. We use EC2 instance roles for our EMR clusters. This greatly simplifies delivery of API credentials into those systems and allows us to cleanly manage security policies for each. It also makes it a lot less likely that someone will check in production API credentials to source control. The new VPC endpoints for S3 are also very welcome. This allows us to further restrict the access to the internet from inside our VPC, and it allows us to lock down those buckets such that they're not accessible to the rest of the world at all. And in addition to all of these layers, we're also using private 10 gigabit direct connect circuits into Amazon so that none of our traffic traverses the public internet at any time. So encryption is actually pretty easy in this day and age, but managing the encryption keys is where all of the complexity lies. We use a cluster of on-premise SafeNet Luna HSM devices to store our master keys, and those HSMs are located in multiple geographically diverse locations. HSMs are specially hardened storage appliances designed only to store encryption keys, and we use the same model as the Amazon Cloud HSM service. Our Redshift clusters are directly integrated with our HSMs, such that when a Redshift cluster boots, it has to reach back to our HSM to decrypt its master key before it's able to read any data, whether that's from a regular table or a snapshot or anything else. We intentionally have these devices in our physical custody so that if there's ever a breach, we can sever the connections to our HSMs and terminate our Redshift clusters, thus making all of the data stored unreadable. In practice, we've never had to take such drastic measures, but it's an integral part of our security mechanism so that we have good data storage security. For all of the data stored in S3, keys are stored in an internally developed KMS, which we've named Vince Clortho after the keymaster of Gozer from Ghostbusters. We publicly describe that system as usually just the Nasdaq KMS, and it's very broadly similar in functionality to the Amazon KMS. And anywhere throughout this talk where I talk about its use, the Amazon KMS could be substituted instead. We keep that KMS ourselves, again, so that we have tight control over all of those encryption keys, and so that we can cut off access physically in the event of a breach. So transparent encryption is possible with objects stored in S3 through what's called the Encryption Materials Provider interface in the S3 SDK. This class is used directly by the S3 client, making it very easy to adapt systems that were already talking to S3 to use encrypted objects instead. This interface is also used as a plugin by EMRFS, which is an HDFS implementation on top of S3 developed for use in EMR clusters. Because that same mechanism is used by the S3 client and by EMRFS, it's easy to interact with encrypted objects in S3 whether or not you're going through HDFS. Whenever an object is accessed in S3, your encryption materials provider will be called on to produce an encryption key for that object. A materials description from an S3 object's user metadata is passed in and can be used to determine what the correct key is to retrieve. And similarly, when you write a new object into S3, that provider interface will be called on to produce both an encryption key and a materials description, which is stamped onto that object in metadata. In our case, we store a token representing the encryption key in that materials description. And that token is not considered sensitive information, since without API credentials and network access to our KMS, it's just random data. So this is great, but what about performance? If we spend all of our time encrypting and decrypting data, when does actual work get done? There's always a penalty for using encryption, and this case is no different. We've seen a roughly 25% performance penalty when encryption is enabled on S3, and this is well within acceptable bounds and similar to the penalty that we've seen in Redshift with encryption. CPUs are actually very good at performing AES operations these days, and in any case, the choice would be for us to either not use S3 or use encryption, and that's a pretty easy choice to make. Most importantly, seeking within an encrypted object in S3 actually works. This is critical for performance because a lot of modern file formats have an internal block structure, and the readers will decode some metadata from the beginning or end of a file and then seek around within that file to actually read the data. The thing to remember here is that this actually just works, and you mostly don't have to take any care to do it. But for it to work, you do need to encode the unencrypted file size on user metadata on each object, and that unencrypted file size is what must be reported back to any layers on top of the storage system. All of the details for seeking within an encrypted object are handled by the SDK itself, and in practice, it will actually read a little bit more data than you're asking it to. When you seek into an object in S3, a new HTTP request is created with a byte range starting at the position that you want to seek to and ending at the end of the file. What actually happens in practice is that if I'm requesting data starting at the blue arrow, the SDK will actually start reading data from the white arrow, which is the beginning of the previous AES block. That's because the AES cipher that's used needs a little bit of information from the previous block to decode the current block. But in practice, it's a very small amount of extra information that needs to be read. You can test this yourself by enabling wire-level debugging in the SDK and then making some requests, and you can see that the byte range that you request is different than the byte range that the SDK is actually requesting from S3. Moving lower into the software stack onto each individual EC2 instance, we needed to encrypt some of the local disks on each node. This is specifically because Presto, like many other systems, uses local disk as scratch space. To satisfy this need, we developed an EMR bootstrap action, or BA, which encrypts a block device under Presto's temp space. This is a fairly straightforward setup using the standard Linux LUX tools and using crypt setup to create an encrypted block device. There's a few gotchas here to make sure that when you reboot the node, it doesn't hang forever waiting for someone to type in an encryption key to the console, but otherwise it's pretty straightforward. Similar to how the S3 encryption provider stores a key token in metadata, we store a key token in a local configuration file. And then on reboot, an init script will use that token to look up the encryption key to decrypt the block device and mount it so that Presto can use it as temporary space. And finally, moving all the way down the stack into the Linux kernel itself, we had to find a way to get SELinux working on EMR. This was certainly more complicated than the encryption, the disk encryption BA, but it's still fairly straightforward. Basically, this script installs the various SELinux packages needed and then tweaks the command line for the kernel in the grub config. It then rebuilds the initRD system image, marks the root file system for SELinux relabeling, and then reboots the node. Rebooting a node from a bootstrap action is not as easy as it sounds, since you can't just call reboot from that script. If you do, you'll either get your cluster marked as terminated because your bootstrap action failed, or you'll get a whole new node because the EMR thinks your node has failed, and you'll get this process starting all over again. So to get around this, we create a simple script in /temp that just sleeps for a few seconds and then reboots the node. So our BA does all of its work and then executes that script in the background as its last step. The result is that our BA completes successfully, the instance controller reports that everything is fine, and then the node spontaneously reboots a few seconds later. This mechanism only works on EMR 3.8, and we're working with the EMR team to get it working in 4.0 as part of an effort to generally harden the base OS in EMR. We're also working on an SELinux policy for Presto, and we'll hopefully be able to share that with the community once we've got it into a good state. So now that I've discussed what we've done to run apps securely on EMR, it's time to discuss Presto, because we do actually want to get access to all of this data. So first, what is Presto? Netflix and others have discussed it at this and previous reInvent conferences, but just as a recap, Presto is an open source MPP SQL database released by Facebook. It's able to query a variety of different data sources through what Presto calls their connector API. Clients connect to the system through either JDBC or ODBC drivers, and Airbnb has released a nice web GUI called AirPal. Specifically for our needs, we're using what Presto calls the Hive connector. In this setup, tables are defined in a Hive Metastore as external tables, with their locations as directories in an S3 bucket. Hive isn't actually used as part of query execution. It's just a way to define the tables, their locations, and how they're partitioned. Presto actually does all of the work of reading data from S3 and processing all of that data itself. So here's a deployment diagram for Presto. You can see on the left, we have SQL clients and our KMS located in a Nasdaq data center. We have Presto, and those clients issue queries to Presto using either direct SQL interfaces or through the AirPal GUI. Presto reads schema definitions from the Hive Metastore, and then it reads data from S3. To decrypt that data, Presto has to reach back to our data center to retrieve encryption keys for each object that it reads out of S3. And then within Presto, that data is decrypted and processed, and then query results are returned to clients just like a normal database. So that sounds easy. How does Presto work on EMR? We're currently using a bootstrap action to download and install Java 8, which is required by Presto, and then to download and install the Presto server itself. This BA is based on the EMR team's Presto BA and adds support for custom encryption materials provider jars so that the Hive connector is able to decrypt data. We also configure Presto to use an external Hive Metastore instead of the one on a local EMR cluster. This is done since we centrally manage our Hive Metastore in a long-running EMR cluster that runs only the Metastore and no actual Hadoop jobs. Currently, we're using EMR 3.8 for these Presto clusters, and again, this is just because we haven't got the SELinux system working on 4.0 yet. We're really excited for the EMR team's new Presto sandbox deployment, and we'll be deploying our security efforts to that system very soon. So I said that our Presto BA was modified to use an encryption materials provider. This leads me to how we get Presto to interact with encrypted data. Presto doesn't use EMRFS for its access to S3, and instead implements its own simple S3 file system on top of S3. We added support for encryption materials providers to the Presto S3 file system class, and these changes were actually fairly trivial to make and limited mostly to that single class. We're in the process of contributing these changes back to our new GitHub account, github.com/Nasdaq, and those changes should be up there in the very near future. We actually just got clearance to do this yesterday. So we'll be working with Facebook to get these changes integrated into the main line of Presto, and that should eventually make its way into the EMR sandbox deployment so that everybody can benefit from our work. This is actually the first time that Nasdaq has contributed back to an open source project on GitHub, and should not be the last time. We've had a really good relationship with our Office of General Counsel, and this effort has support from the executive level within Nasdaq. And similar to our changes that we made to Presto, we're also making changes to AirPal to support encryption and compression on data that it unloads to S3. So now that I've discussed how we get data into S3, how we get it back out using Presto, it's time to talk about the actual data formats in use. There's really two popular file formats for row-oriented data in Hadoop, Parquet and Orc. Both are compressed columnar storage formats, meaning that column values are adjacent to each other within the file instead of rows being packed next to each other. There's a variety of reasons why columnar formats are good, and that's beyond the scope of this discussion. Both formats store highly structured, schema-validated data, and both are supported by a variety of Hadoop applications. And there's arbitrary user metadata that can be encoded on each file. So Orc has some advantages for us, mainly that date and timestamp types are fully supported in Hive and Presto. Since we're on a daily cadence driven by the exchanges that we support, and since most of our data are time series, this is a big advantage for us. The downside is that there's rigid schema ordering requirements for the columns in an org file. Specifically, columns in that org file are addressed by position instead of by name. So the columns defined in your Hive table need to match exactly the order that they're defined in your actual org files. So this issue is compounded for us since we partition our data, and since partition columns end up logically at the end of a file, or end of a schema, this became a real issue for us. The Java API for encoding org files is also a bit clunky, but the thing that really killed it for us is that we experienced terrible performance on org once encryption was enabled. We didn't dig into this too deeply, but in all of our tests, we saw between 15 and 18x slowdown and went from around a gigabyte a second scanned in our 2-node cluster to less than 70 megabytes a second scanned. So unfortunately, that was really a deal breaker for us. For us, the winner is Parquet. It enjoys wide support from a number of different projects, Presto, Spark, and Drill, just to name a few. It's actively being developed, and adoption is increasing. Schemas are more flexible. Columns are addressed by their name instead of by position, which doesn't sound like much, but it actually makes managing schemas on top of these files a lot cleaner and easier. For Presto, you do have to set hive.parquet.use column names to true in your Hive config, but that's pretty easy. Our testing also revealed acceptable performance when encrypted, right in line with the slowdown that we've seen just with using S3. And thankfully, the Java API is nice and clean. It was fairly easy for us to adapt our generic data flow framework to translate our schema definitions into Parquet type definitions, allowing us to easily encode all of our data as Parquet. However, Parquet is a new file format, and it still has some rough edges. All of these issues are being actively addressed by the community, but right now, date types are not supported by Hive or Presto. Parquet itself has a date type, but Hive and Presto won't deal with them specifically in Parquet files. So dealing with all these different projects, you end up with a sort of Venn diagram of file formats, Hive schema types, and query tools, and we have to learn how to operate within the intersection of that diagram. So it's a little annoying, but it's easy enough to deal with. We transparently encode dates as integers and basically do a transformation where we remove the dashes from a date and interpret the result as an integer. This allows us to still order by those columns and easily translate them. Timestamp columns are converted to big integers, which is the Hive equivalent of a 64-bit long. The timestamp type in Parquet is actually only accurate to a resolution of milliseconds anyway. And since in practice, when we have higher resolution timestamps, what we end up doing is encoding a date column and then a separate nanoseconds since midnight column, which is then used for high resolution ordering. So this brings me to schema and data management. The Hive Metastore is the system of record for Presto as far as what tables exist, their locations, and how they're partitioned. We deploy an EMR4 cluster for our Metastore. 4.0 makes it a lot easier to talk to the Metastore through Thrift, which is how Presto communicates with the Metastore. This cluster is run in our central warehousing account, the same account with the S3 bucket containing all of our data. That cluster is reachable by client accounts through VPC peering, so that client accounts don't have to manage their own Metastore, though they're free to do so if they have testing requirements or if they want to experiment with data that's only available in their account. We're backing that Metastore with a RDS for a MySQL database, which makes for easy backups and management. And we also are using encrypted storage there. Now, in this case, encrypted storage isn't as critical since we're just storing schema definitions and table locations in S3, and that's not exactly a trade secret. The other reason that this Metastore is deployed centrally is that our ingest system actively is managing schemas in that Hive Metastore, and will automatically create new tables as we see new data coming through. New partitions are created each day, and that Hive Metastore is modified to add those new partitions. Additionally, since we're able to detect schema changes from upstream systems, we can automatically create new tables as we see new versions of those tables. So I mentioned that we version our table schemas. So what exactly does that mean? We store data in an S3 bucket in a pretty straightforward layout. Basically, there's a directory structure with schemas at the top, and then with tables underneath those schemas. Within each table directory, there's a directory for each logical version of that table, and then within each version, there's a directory for each data partition. Those data directories are named using the standard Hive naming convention, and this lets us recover partitions using the msck repair table command in Hive. Now, we don't normally use this to recover partitions, since we're actively managing them throughout the day, but it's useful if we're creating a new Metastore for testing or if we need to recreate it from scratch. When we detect a schema change, we increment that version number, and new data is written into a new location in S3, and the old location is essentially abandoned from a data ingest perspective. We raise alerts so that humans can intervene and figure out what to do about a migration, and in practice, we usually get notified about these changes ahead of time and can plan accordingly, but that doesn't always happen. We're also not in such a dynamic environment that we're doing migrations every day, so in practice, this happens fairly infrequently. But when those changes do occur, we have a number of tools to migrate the old version of a table into the new version of a table. So one lesson that we've learned from operating in that intersection of the Venn diagram on the previous slide is that we need to manage a logical and a physical schema for each table. Given the data type transformations, such as date to integer, etc., we can't directly compare our Hive schemas to Redshift or other source databases to determine if there's been changes. So we use the logical version of a schema to compare to the source data, and we use the physical schema to produce Hive DDL for tools like Presto to interpret. Those schema definitions are stored in a local MySQL database, where we perform all version management and where we track the locations of those tables in S3. We have a few simple tools to export these schemas as Hive DDL scripts. And normally, again, that's not used because we actively manage that Hive Metastore, but it's useful if we had to, for instance, recreate our entire Metastore from scratch in production. So Orc and Parquet both support file-level metadata, and we use this to encode a variety of information about the data contained in each of those files. We encode the definition of the partition columns there, the time zone the file was originally produced in. We encode the name of the table and the current and original schema version of that table. We also encode a representation of all the data type transformations that were performed on data in that file. All of this is so that we can recreate the logical versions of the schema and the data in that file, undoing any of the transformations performed while writing it. This allows us to go back and reprocess data which may have been corrupted because of a problem in migrations, and it also lets us just figure out what happened all along the way. By looking at the current and original schema version, we can know if a file was migrated or not, and from which versions. So some of this borders on paranoia, but we wanted to make sure that we had multiple overlapping mechanisms to prevent us from losing data or losing meaning or resolution of that data. After all, this is meant to be a very long-term store for all of our data, and we can't lose anything. So I've mentioned table partitioning a few times, and it plays into our methodology for data management. We partition basically all of our tables by date. This is going to be different for different use cases, but since we're driven by exchanges that are on a daily cadence, and since all of our records have a reference date stamped on them, it makes sense for us. All of our data, aside from reference information, is also a time series, so this all fits together. Partition definitions really help query performance drastically, since it cuts down very much on the amount of data that you need to scan out of S3 to satisfy any given query. If you've got years of data stored, there's no reason to scan all of it if you know that what you're looking for occurred on a particular date or within a particular range of dates. Another pointer is to use backticks in your Hive schema DDL. This will let you use reserved words or really any Unicode string as a column name. We also noticed that Presto will return nulls for values if the column name isn't lowercase in your actual Parquet files, so that's something else to look out for. And in cases where we do have to go back and correct data, what we've chosen to do is correct it in Redshift using SQL, again because we're a SQL-centric shop and it's easy. We then unload that data from Redshift into S3 and then reprocess it into Parquet files to replace the existing, apparently corrupt files. We've developed a number of command line tools that make it easy for us to deal with large blocks of data coming out of Redshift and being retranslated into Parquet files into S3. And those tools manage the schemas all along the way. We've also developed a number of tools for dealing with data in S3 and Redshift. We've got tools that can extract some or all data out of various legacy databases to produce CSV files suitable for ingest into this system. For legacy databases, it basically just executes a series of SQL commands to extract data for each partition that we want to move. And for Redshift, it'll issue unload commands to move that data into S3. Once we've extracted schema information and CSV data from those databases, we use those command line tools to bulk convert data into Parquet. Those tools can write directly into the encrypted S3 buckets, placing the data in the correct directory structure based on the schema, table, version, and partitioning information. This allows us to easily move data in and out of this S3 warehouse, and we're able to do it billions of rows at a time. We developed these tools basically because we want to encode all of that extra metadata on each file, and because we wanted to have tight control over how every field is converted into each of these formats. We had initially experimented with using Hive or other mechanisms to select out of a CSV back table and into a Parquet back table, but that didn't really give us the level of control that we were looking for. And finally, we developed some custom tools to migrate Parquet files. These tools basically read in version n of a table and write out version n+1. Most of these migrations are pretty trivial and just scripted up, such as adding a new column with or without a default value, or renaming and moving columns around. These had to be developed, again, because we're using all of that custom metadata, and because we didn't want to take the chance of losing data because of an errant in-place migration. Most of our migrations are trivial and just scripted, like I said, but in some cases we have to write Java code if we're splitting an existing column into multiple other columns or performing some more complicated migration. This is again why we track the current and original schema version on each file, so that we can know exactly what happened to it every step of the way. And we don't have to track any of that information in some external database or anything like that. It's contained directly on each file. So this actually brings me to the end of this presentation, and I'll take a few moments to review and then discuss future directions for our efforts. Today I discussed our motivations for extending our Redshift warehouse using EMR and S3. I talked about how our data ingest system works, how we're able to query encrypted data stored in S3 using Presto and other Hadoop applications, and how we perform how we manage our schemas and perform migrations on those schemas. And a few lessons to take away from this. This is the TLDR version of the presentation. You should manage your storage and compute resources separately, especially if you're dealing with a long-term data store where much of your data is either cold or warm. It's okay to be paranoid about data loss, and you should implement as many overlapping policies and procedures as you think is suitable for your needs. S3 encryption is pretty easy, and seeking within an encrypted object actually works. We chose Parquet over Orc as our storage format, mostly because of the encryption performance, but also because of growing industry support for Parquet. You should partition the data in your tables and track versions of those tables, both from a performance perspective and a paranoia of losing data perspective. You should manage logical and physical schemas of those tables, because you might have to do data type translations, and because it'll make it easier to compare with source systems to see if there's been changes. And finally, you should do some thinking about data management and automation tools, because you'll be moving a lot of data around. So finally, let's talk about some enhancements that we'll be making to this system over the next year. We'll be archiving original source data in this system for SEC 17A4 compliance. This is the so-called books and records requirement. That'll be using the new Glacier Vault Lock feature, which is basically worm storage on top of Glacier. And this is driven directly out of the fact that we're in a very highly regulated environment. We'll also be decoupling our data retrieval and data processing systems over the next year. I'd mentioned that we want to move a lot of this processing into EC2, and that's going to be our way of doing it. Currently, that ingest system sits on-premise because it has to have elevated access rights and network connectivity into a wide array of different systems inside Nasdaq. If we split that system in two, we'll leave part of it behind so that it can still have elevated access rights into those other systems, and it'll just park encrypted data in S3. The rest of the systems can then operate entirely in Amazon and only deal with files in S3. And they don't have to deal with internal routing or any other issues. Another part of that move will be to migrate our workflow engines database to Amazon Aurora, where we'll have a more resilient and more durable store for all of that information. We'll also be leveraging more non-SQL frameworks such as Spark and machine learning. And finally, we'll be adding near real-time streaming ingest, more and more data sources, including some truly high-volume data feeds. Remember to complete your evaluations and have a great time at the party tonight. Thank you all for your time.